Today, we are embarking on a journey far deeper into the past than most of us ever imagine. Not just millions of years, but billions. Not just to the time of dinosaurs or mammoths, but to an Earth unrecognizable, long before the rise of Pangea, the famous supercontinent that would dominate the late Paleozoic and early Mesozoic worlds. When we hear the word Pangea, it often conjures images of all the continents fused into a single massive landmass, a global puzzle locked together, dinosaurs roaming across endless forests, giant deserts stretching for hundreds of miles, a connected world where creatures could walk from what would one day be North America all the way to Africa without crossing an ocean. But tonight, our story does not dwell on Pangea itself. Instead, we peel back even more layers to the eons before it existed. Because before Pangea, there were other supercontinents, and before those, there were fragments, proto-continents drifting in young oceans, sometimes colliding, sometimes breaking apart. The Earth we will discover together was often alien. It was a world of molten rock, poisonous skies, and later, a planet of simple microbial life clinging to existence in shallow seas. It was a place where land was bare, lifeless, and quiet for billions of years before the first green shoots took hold. This is the story of what Earth was like before Pangea, a tale stretching from the planet's fiery beginnings through the cycles of ancient supercontinents like Columbia and Rodinia, to the astonishing burst of life in the Cambrian and beyond. We will not rush. Instead, we will move slowly, step by step, as though walking through the halls of a vast museum where each gallery represents an epoch of unimaginable time. With each step, Earth itself changes shape. Continents wander, seas expand, climates shift, and life finds new ways to endure. Close your eyes, if you wish, and imagine Earth without cities, without humans, without even the continents as you know them. Imagine an alien sky, a strange ocean, a surface still being written by fire, water, and stone. That is where our journey begins. If we are to understand what Earth was like before Pangea, we must travel not just hundreds of millions of years into the past, but billions, to the very beginning when the young Earth was still forming. The Hadean Eon, beginning about 4.6 billion years ago, was not a time when anyone would have wished to visit. The name itself, Hadean, comes from Hades, the underworld of Greek mythology, and with good reason. Earth was a violent molten place, a ball of rock still glowing from the heat of its creation, scarred by relentless bombardments from space. In these early ages, Earth's surface was unstable. Vast oceans of magma churned and boiled, broken by constant impacts from asteroids and comets left over from the formation of the solar system. The moon itself was born from one of these cataclysms, when a Mars-sized body called Theia collided with the infant Earth, The debris thrown into orbit coalesced into our lunar companion. The scars of that unimaginable impact are written not only on the moon's surface, but in Earth's tilted axis, its rotation, and even the tides that still shape our oceans. The air was thick with volcanic gases, carbon dioxide, methane, ammonia, sulfur compounds. No oxygen yet. The sky was probably red or orange, tinted by the haze. Rain fell as steam boiled away, evaporating before it could settle. And yet, even in this inferno, the seeds of habitability were being sown. As millions of years passed, Earth began to cool. The crust thickened, rain condensed, and no longer vanished instantly. Water pooled, gathered, and at last, true oceans began to form. Imagine standing on a barren coast of volcanic rock, black basalt stretching to the horizon. Clouds hang heavy in the sky, and rain lashes the surface in endless storms. Lightning cracks and thunder rolls, echoing across a world without trees, without animals, without birds. Only water, stone, and fire. These first oceans may have been tinted green or brown, loaded with dissolved minerals and metals leached from the crust. Beneath their surfaces, chemistry was quietly at work, setting the stage for something remarkable, the origin of life. But before life could spread, Earth itself had to take shape as a stable planet. This brings us into the Archean Eon, beginning around 4.0 billion years ago and lasting until about 2.5 billion years ago. It was during this vast stretch of time that the first continents emerged. In the beginning, Earth's crust was thin and fragile, constantly recycled by the restless heat below. But over millions of years, portions of it thickened. Islands of granite, the first proto-continents, rose above the oceans. They were small at first, scattered like stepping stones across the seas. Yet they were different from the oceanic crust around them, lighter, more buoyant, and able to resist sinking back into the mantle. From these beginnings, continents would grow. Slowly, through processes of plate tectonics, volcanic eruptions, and collisions, these landmasses merged, broke apart, and reformed again. Long before Pangea, Earth had already assembled and dispersed several supercontinents. Names like Valbara, Ur, and later Keenorland echo as ghostly memories of lands lost to time. They were not as vast as Pangea would one day be, but they were the ancestors of the continents we know today. Meanwhile, life had begun its quiet revolution. In the Archean oceans, simple cells, prokaryotes, took hold. Perhaps they emerged in warm tidal pools, perhaps at the mouths of hydrothermal vents, where mineral-rich fluids gushed into the sea, creating pockets of chemical energy. Wherever it happened, the spark of biology lit a flame that would never again be extinguished. At first, life was invisible, microbes too small for the eye, floating in the water or clinging to mineral surfaces. But even these tiny organisms began to leave their mark. In shallow seas, mats of cyanobacteria built layered structures called stromatolites, rocky mounds that still exist in places like Shark Bay, Australia, and are among the oldest fossils on Earth. They are living echoes of a time billions of years ago, when life was just beginning to reshape the planet. The Archean world would have looked strange to us. The continents, bare and lifeless, were streaked with volcanic mountains and cut by rivers carrying greenish waters. The air was thick with carbon dioxide and methane, likely creating a greenhouse effect that kept the planet warm despite the sun being dimmer than it is today. The skies may have been hazy, even orange. Oceans shimmered under alien light, full of microscopic pioneers. There were no forests, no animals, not even moss or grass. Only rock, water, sky, and the silent labor of microbes breathing, dividing, and laying the groundwork for everything that would follow. It is humbling to think that from such humble beginnings, Earth would one day host dinosaurs, mammoths, and eventually us. But at this stage, the greatest drama was still the slow cooling of the planet, the rise of the continents, and the persistence of life against the odds. By the close of the Archean, continents had grown larger. Plate tectonics was firmly at work, and life was spreading in the oceans. The stage was being set for the next act in Earth's pre-Pangea story, the Proterozoic Eon, when oxygen would begin to transform everything, and when the first great supercontinents would rise and fall. The Archean Eon closed with the Earth already transformed. Continents had emerged, small and scattered. Microbial life flourished in the oceans. The stage was set for one of the most profound transitions in the history of our planet, the Proterozoic Eon, which began about 2.5 billion years ago and lasted until 541 million years ago. Nearly 2 billion years long, it was an age of tectonic assembly, chemical revolutions, and biological innovations that laid the foundation for the complex worlds to come. Compared to the chaotic Archean, the Proterozoic was a calmer time in many ways. The planet's crust had thickened, plate tectonics became more predictable, and continental landmasses stabilized. Volcanism still shook the earth, mountains still rose and fell, but the planet was now operating on cycles that would be recognizable even today. And yet, this eon was anything but uneventful. It saw the rise and fall of supercontinents, vast assemblies of land that gathered, split, and reformed across immense spans of time. It also witnessed the Great Oxidation Event, when oxygen, once scarce, flooded the atmosphere, forever changing the chemistry of the oceans and the destiny of life. If Pangea was the most famous supercontinent, it was not the first. Long before its time, Earth had already built and dismantled several global landmasses. Among them, Valbara, possibly the first supercontinent, forming as early as 3.1 billion years ago. Ur, a smaller protocontinent, perhaps the oldest surviving continental core, dating back 3.0 billion years. Land, emerging around 2.7 billion years ago, one of the first truly global-scale supercontinents. Columbia, also called Nuna, forming around 1.8 billion years ago. Rodinia, assembling about 1.1 billion years ago, a massive landmass that predated Pangea by hundreds of millions of years. These supercontinents were the great experiments of plate tectonics, testing how land could unite and fracture under the forces of Earth's interior. But while continents shifted and oceans spread, something far more subtle and far more consequential was happening in the air. For much of Earth's early history, the atmosphere was nearly devoid of oxygen. Life existed, but only in the form of microbes that thrived without it. That began to change, thanks to tiny architects of the biosphere, cyanobacteria. Through photosynthesis, these organisms absorbed sunlight, water, and carbon dioxide, and released oxygen as waste. At first, this oxygen was absorbed by iron in the oceans, creating vast deposits of banded iron formations that still mark the geologic record. But eventually, around 2.4 billion years ago, the system was saturated. Free oxygen began to build up in the atmosphere in what is known as the Great Oxidation Event. The consequences were enormous. For anaerobic microbes, oxygen was toxic. Many lineages perished or retreated to oxygen-free environments. But for others, it opened new chemical pathways, including aerobic respiration, which is far more efficient than anaerobic metabolism. This set the stage for more complex life forms, though they would not appear for many millions of years. The skies too changed. Methane levels dropped, greenhouse effects weakened, and Earth may have plunged into its first snowball Earth episodes, periods when ice extended close to the equator. Imagine looking at the planet from space. Continents gleaming white with glaciers, oceans sealed beneath sheets of ice, the world caught in a deep freeze. It is astonishing to think that a microscopic shift in ocean chemistry could lock the entire Earth in ice. Throughout the Proterozoic, the continents were never still. They assembled into vast supercontinents, only to fragment and scatter again. Land, one of the earliest, formed around 2.7 billion years ago. It may have been Earth's first attempt at global unity, stretching across much of the planet. But it would not last. By 2.1 billion years ago, it had broken apart, leaving fragments drifting into new configurations. Later came Columbia, also known as Nuna, around 1.8 billion years ago. Columbia endured for several hundred million years, its land masses sprawling across the equator and beyond. With stable cratons at its heart, Columbia may have hosted the first great mountain ranges, raised as continents collided. And then, around 1.1 billion years ago, a new supercontinent emerged, Rodinia. Its very name means to give birth in Russian, reflecting its central role in Earth's story. Rodinia was enormous, covering much of the globe. Some reconstructions place it with modern North America at the core, joined by pieces of what are now South America, Africa, and Australia. Rodinia endured for hundreds of millions of years, shaping climate, currents, and ecosystems. While continents collided above, life below the waves remained mostly microscopic. Cyanobacteria and other prokaryotes ruled the seas, building stromatolites and reshaping the atmosphere. But around 1.6 to 1.2 billion years ago, a profound innovation occurred. The first eukaryotic cells appeared. Unlike simpler bacteria, these cells had nuclei, internal structures, and a capacity for complexity. They were the ancestors of all plants, animals, and fungi. The oceans of the mid-Proterozoic may have been filled with these pioneering eukaryotes, algae-like organisms floating in the water, absorbing sunlight. It was a quiet revolution, one that would eventually lead to the multicellular life forms of the Ediacaran and Cambrian. Still, for most of the Proterozoic, Earth's landscapes were barren. Continents stood empty, their surfaces sculpted only by wind, rivers, and glaciers. No forests, no carpets of grass, not even a patch of moss. To imagine them is to picture endless rocky plains, broken by mountains and volcanoes, surrounded by shallow seas, alive with microbial mats. As Rodinia assembled, Earth's climate swung wildly. Some evidence suggests the world entered repeated snowball Earth episodes. Frozen nearly from pole to pole, life endured, clinging to refuges near hydrothermal vents, open waters, or beneath the ice. And yet, somehow, it survived and even thrived. By the close of the Proterozoic, oxygen levels were higher, eukaryotes were diversifying, and the stage was set for the most astonishing transformation yet. The rise of large, multicellular organisms in the Ediacaran period, leading into the Cambrian explosion. The continents had wandered, assembled, and scattered many times already. Pangea was still far in the future, but the Proterozoic had given Earth its first real taste of continental unity, atmospheric oxygen, and complex cellular life. It was, in many ways, the rehearsal for everything that followed. Life on Earth began as something so small, so fragile, that for billions of years it was invisible to the eye. If we were able to step back into the oceans of the Archean or Proterozoic, there would be no fish, no plants, no animals, only a cloudy haze of microbial life, so subtle that the seas might look empty to us. And yet, those tiny pioneers were slowly reshaping the entire planet. For much of the Archean and early Proterozoic, the world was ruled by prokaryotes, simple, single-celled organisms without nuclei. These included bacteria and archaea, masters of survival who thrived in environments ranging from volcanic vents to shallow seas. Among them, cyanobacteria played the most transformative role. They captured sunlight through photosynthesis, producing oxygen as a byproduct. What began as invisible bubbles rising into the sea would ultimately alter the very chemistry of Earth's oceans and atmosphere. The Great Oxidation Event, which we explored in the Proterozoic, was their doing. Their activity is preserved in stromatolites, layered mounds of mineralized microbial mats. Picture a shallow lagoon billions of years ago, its floor carpeted with colonies of cyanobacteria. Day after day, they captured sunlight, trapping sediments and building stony domes that rose from the seabed. These stromatolites were among the first cities of life, vast microbial constructions, some stretching for hundreds of meters. Though simple, they were persistent. Stromatolites flourished across Earth for billions of years, peaking during the Proterozoic. Even today, a few lonely survivors remain in places like Shark Bay, Australia, where they still grow, almost unchanged, as living relics of Earth's most ancient engineers. Around 1.6 to 1.2 billion years ago, a profound innovation occurred. Life took a new form, the eukaryotic cell. Unlike prokaryotes, eukaryotes had nuclei to house DNA and complex internal structures, organelles, that allowed for greater efficiency and specialization. Mitochondria, the cell's powerhouses, were themselves descendants of ancient bacteria that had once been engulfed by larger cells in a remarkable act of symbiosis. Instead of being digested, they formed partnerships, providing energy to their hosts in exchange for protection. This event, known as endosymbiosis, was one of the most important in all of evolutionary history. It gave rise to the ancestors of plants, animals, fungi, and countless other lineages. Every oak tree, every whale, every mushroom, every human, each traces its origin back to this union of ancient cells. In the oceans of the mid-Proterozoic, eukaryotes began to spread. Some resembled algae, drifting in planktonic blooms. Others lived attached to surfaces, forming colonies. For the first time, cells could become larger, more complex, and eventually capable of working together. From single eukaryotic cells, the leap to multicellular life was not inevitable, but it did happen. Small colonies began to cooperate, sharing tasks and resources. Some cells specialized in movement, others in reproduction or nutrient storage. Imagine a shallow bay 1.2 billion years ago. The water glimmers in the Proterozoic sunlight, and beneath the surface float colonies of red algae, among the earliest known multicellular organisms. They are simple, no more than filaments or sheets of cells, but they mark the beginning of a trend that will one day lead to towering forests and vast animal kingdoms. These early multicellular forms were fragile, ephemeral, yet they were also experiments, nature's first trials in complexity. Each step forward created new opportunities for diversity. On land, the earth remained barren. The continents of Rodinia loomed above the seas, bare rock broken by mountain chains and rivers. Winds swept across empty plains. Without plants, soils had not yet formed. Rain fell directly onto naked stone, carving it into valleys and carrying minerals to the oceans. It is hard to imagine today an earth without green, without the sound of rustling leaves or the hum of insects. Only silence, broken by the hiss of wind and the rumble of volcanoes. But in the oceans, the story was very different. Beneath the waves, life was innovating. Slowly, steadily, it was building the complexity that would one day transform even the land. By 800 million years ago, eukaryotes were diversifying. Some may have formed simple food webs, with predators feeding on smaller microbes. For the first time, ecological interactions beyond simple competition began to take shape. Still, for most of this time, life remained microscopic. The oceans were alive with invisible drama, but the continents above remained empty. The world was waiting for oxygen levels to rise high enough, for genetic innovations to accumulate, and for ecosystems to reach a tipping point. That tipping point came at the end of the Proterozoic, in the Ediacaran period, when large multicellular organisms finally appeared. But before we reach that moment, we must pause to reflect on the long quiet of Earth's early biosphere. For nearly 3 billion years, life was small. For nearly 3 billion years, it was microbial. And yet, without that patient foundation, without the persistence of stromatolites, without the partnership of eukaryotes and mitochondria, without the slow crawl toward multicellularity, none of what came later would have been possible. Life's dawn was quiet, but it was also unstoppable. The Proterozoic eon drew to a close after nearly 2 billion years of microbial dominance. For most of that time, the oceans were filled only with single-celled organisms or fragile colonies, while the land lay barren and empty. But in the final chapter of the Proterozoic, something extraordinary happened. The Earth entered the Ediacaran period, a span of time from about 635 to 541 million years ago, and life made its first visible mark upon the world. Before the Ediacaran began, Earth endured one of its most extreme climates. During the Cryogenian period, the planet may have been locked in global glaciations, snowball Earth events, when ice reached nearly to the equator. Oceans froze at the surface, continents lay buried under glaciers, and sunlight reflected off vast white expanses. How life survived is still a mystery. Perhaps microbes persisted near volcanic hot springs, in cracks beneath the ice, or in small oases of open water. However they endured, when the glaciers finally retreated, Earth emerged transformed. Rivers carved fresh valleys. Glaciers dropped their loads of rock and debris, and oceans received new pulses of nutrients washed in from the land. This post-glacial world may have been a cradle for innovation. Oxygen levels rose, climate stabilized, and ecosystems became more favorable for larger, more complex organisms. Out of this recovery came the first macroscopic life forms. Around 575 million years ago, in shallow seas across what are now Namibia, Newfoundland, Russia, and Australia, large multicellular organisms appeared for the first time in Earth's history. These were the Ediacaran biota, a collection of strange, soft-bodied creatures unlike anything alive today. Some resembled ferns or feathers, anchored to the seafloor and swaying gently in currents. Others were flat, quilted discs pressed against the sediment. Still others were tubular, branching, or shaped like segmented fronds. Among the most famous are Charnia, frond-like organisms with delicate, leaf-shaped bodies rooted to the seafloor. Dickinsonia, oval, ribbed creatures that sprawled across sediments, possibly gliding slowly to feed. Sprigina, a segmented form, once thought to be an early ancestor of arthropods or worms. Fractofusus, branching, fractal organisms that spread in patterns across the sea floor. To us, they seem alien. They left no skeletons or shells, only impressions preserved in sandstone. Their biology is still debated. Were they early animals, fungi, giant protozoa, or representatives of an entirely extinct kingdom of life? Whatever they were, they marked a profound shift. Life had finally grown large enough to be seen with the naked eye. Picture an Ediacaran seafloor. The water is shallow, lit by sunlight filtering through waves. The ground is firm, made of sand or silt, not yet churned by burrowing animals. Across this surface spread communities of soft-bodied organisms. Charnia fronds rise like alien ferns in an undersea garden. Dickinsonia lie flat against the sand, patterned like living rugs. Fractofusus spreads in clusters, repeating its fractal patterns. There are no fish, no shells, no predators as we know them. The ecosystem is quiet, peaceful, and almost static. Organisms absorb nutrients from the water or sediment. Some may photosynthesize, others may filter feed. Movement is rare, limited to slow gliding or drifting. Yet even in this calm world, interactions were emerging. Dickinsonia grazed microbial mats, leaving feeding traces behind. Fractofusus spread across the seafloor in sprawling colonies. These were the first stirrings of ecological complexity, organisms competing for space, light, and resources. What were the Ediacaran organisms? This remains one of the great puzzles of paleontology. Some researchers argue they were early animals, primitive ancestors of groups like sponges, cynodarians, or even bilaterians. Others suggest they were unrelated to animals altogether, perhaps representing an entirely unique experiment in multicellular life. The truth may be a mix. Some ediacaran forms could indeed be ancestors of later animals. Others may have been evolutionary dead ends, strange experiments that left no descendants. What is clear is that the ediacaran world was a laboratory of possibilities. Life was trying out new forms, new strategies, new ways of being multicellular. Some of these strategies would vanish, while others would set the stage for the explosion of diversity that followed in the Cambrian. The ediacaran biota flourished for tens of millions of years. But as the Cambrian approached, most of them disappeared. Their extinction may have been due to the rise of new predators, changes in ocean chemistry, or the spread of burrowing animals that disturbed the sea floor habitat they depended upon. When the Cambrian dawned, a new world opened, one of skeletons, shells, eyes, and movement. Compared to this, the ediacaran biota seemed fragile and otherworldly, and yet their significance cannot be overstated. They were the first visible life forms on Earth, the first forests of fronds, the first carpets of creatures covering the sea floor. They marked the moment when life grew bold enough to reshape ecosystems on a macroscopic scale. As the ediacaran period closed around 541 million years ago, Earth was ready for transformation. The continents of Rodinia had broken apart. Oceans circulated with fresh currents. Oxygen was abundant, and ecosystems were primed for innovation. The long, quiet reign of microbes and soft-bodied pioneers was about to give way to something astonishing. The Cambrian explosion, when animal life erupted into diversity, filling the seas with predators, prey, and complex food webs for the first time. The ediacaran world was a dreamlike prelude, a time of strange, quilted organisms drifting in calm seas. What came next would be more dynamic, more dramatic, and more familiar to us. The beginnings of animal life as we know it. The Ordovician had ended in catastrophe. Vast ice sheets had spread across the southern reaches of Gondwana, locking up seawater, lowering global sea levels, and devastating marine habitats. Nearly 85% of all marine species had perished, victims of dramatic climatic swings that Earth had rarely seen before. Yet, as history has shown time and again, life is resilient. From devastation comes renewal, and in the wake of the second great mass extinction, a new world began to take shape. The Silurian world. The Silurian period, spanning from about 443 to 419 million years ago, was a time of stabilization, recovery, and expansion. Compared to the turbulence of the Ordovician, Earth now entered a warmer, more stable climate. Glaciers retreated. Sea levels rose again, drowning continental shelves and creating shallow seas teeming with life. These seas became cradles of evolution, fueling the growth of vast reef systems, the diversification of marine species, and, most significantly, the quiet but revolutionary spread of plants across the continents. The oceans, still reeling from the Ordovician extinction, slowly filled with life once more. Corals, which had been nearly extinguished, staged a remarkable comeback. New reef ecosystems formed, dominated by tabulate corals and stromatoporoids, sponge-like reef builders that secreted massive limestone structures. These reefs stretched for kilometers, forming some of the largest reef systems in Earth's history. In their shadow swam early fish, trilobites, cephalopods, and eurypterids, the fearsome sea scorpions. Among these eurypterids were some of the largest arthropods ever to exist. Certain species grew to more than 2 meters in length, armed with spiny appendages for capturing prey. They were formidable hunters, patrolling shallow waters and estuaries, symbols of Silurian dominance. In the oceans, nautiloid cephalopods continued to thrive, their coiled shells allowing for buoyancy control as they glided through the seas. Graptolites, tiny colonial animals encased in delicate skeletons, persisted as well, leaving behind intricate fossil patterns that geologists still use to date Silurian rocks. But perhaps the most significant evolutionary leap of the Silurian seas came with the fish. Before this time, vertebrates had already existed, represented by jawless fish known as agnathons. They were armored, eel-like creatures with bony plates covering their heads, scraping algae and organic matter from the seafloor. In the Silurian, however, nature unveiled something extraordinary: the first-jawed fish, the gnathostomes. With jaws, these fish could grasp, bite, and tear prey. This simple innovation reshaped the balance of ecosystems forever. For the first time, vertebrates became active predators rather than passive grazers. Among them were the acanthodians, often called spiny sharks, though they were not true sharks. They were small, agile swimmers, with spines supporting their fins, darting through reefs in pursuit of plankton and small invertebrates. Their emergence foreshadowed the great age of fishes to come in the Devonian. While oceans brimmed with recovery, a quieter revolution was unfolding on land. For billions of years, Earth's continents had been barren deserts of rock and sand, shaped only by wind and water. But in the Silurian, green began to creep across this stony canvas. The first land plants were simple, lacking true leaves, roots, or flowers. They were small, moss-like organisms, clinging to damp soils and riverbanks. These pioneers included genera like Cooksonia, often regarded as the earliest known vascular plant. Standing no more than a few centimeters tall, Cooksonia's thin stems bore spore capsules at their tips. Yet this unassuming plant carried the seeds of a revolution. the vascular system, tubes that allowed water and nutrients to travel through its tissues. With vascular systems, plants could grow taller, expand inland, and colonize drier environments. They began stabilizing soils, trapping sediments, and slowly transforming landscapes. By doing so, they changed not only the surface of continents, but also the composition of the atmosphere. Through photosynthesis, these early plants released oxygen and absorbed carbon dioxide, subtly influencing climate and paving the way for more complex ecosystems. Plants were not alone in their pioneering journey. The Silurian also witnessed the first known arthropods venturing onto land. Among them were primitive relatives of millipedes and centipedes, feeding on decaying plant matter. The fossil record hints at early scorpions as well, some of which may have still returned to the water, but were increasingly capable of surviving in terrestrial environments. Imagine the scene: small, spindly plants rooted in damp soils, their spore capsules releasing tiny grains into the wind. Crawling among them were the earliest land arthropods, armored bodies low to the ground, seeking shelter beneath rocks and feeding on the detritus of this new world. These humble interactions mark the beginning of terrestrial ecosystems, fragile yet full of potential. The Silurian world was not only biologically dynamic, but also geologically active. The continents were arranged differently than today. The large southern supercontinent, Gondwana, still dominated much of Earth, sprawling across the southern hemisphere. To the north lay smaller landmasses such as Laurentia, ancestral North America, Baltica, ancestral Northern Europe, and Avalonia, a microcontinent that would later collide with them. During the Silurian, these northern continents began drifting toward one another. Collisions between Laurentia, Baltica, and Avalonia sparked the Caledonian orogeny, a mountain-building event that created ranges across what is now Scotland, Scandinavia, and parts of North America. These rising mountains testified to the slow march of continents, setting the stage for the eventual unification that would culminate in Pangea hundreds of millions of years later. The climate itself was warm and stable compared to the icehouse conditions of the preceding Ordovician. Sea levels rose, flooding continental margins, creating shallow epicontinental seas. Coral reefs flourished in these tropical waters, while terrestrial habitats expanded under the influence of greenery. Taken together, the Silurian was a bridge, a period linking the devastation of the Ordovician with the flourishing of the Devonian. It was a time when Earth stabilized, when ecosystems rebuilt themselves, and when crucial evolutionary innovations, jaws, vascular systems, and terrestrial arthropods laid the foundation for the complex web of life to come. It is easy to underestimate the Silurian. Its plants were small, its animals primitive compared to later ages. Yet without the Silurian, the great forests, ecosystems, and vertebrates of later eras would not have been possible. The first step onto land, however small, was the first step toward terrestrial biodiversity. The first jaw, however simple, was the beginning of predator-to-prey dynamics that continue to define ecosystems today. The Silurian world was alive with possibility. Its shallow seas shimmered with coral and fish. Its coasts and riverbanks, once barren, now bore the first hints of green. Its skies carried the spores of plants and the faint stirrings of atmospheric change. And from this fertile foundation, Earth marched toward an even greater chapter, the Devonian period, the true age of fishes, where life would flourish in water and venture boldly onto land, reshaping the planet forever. The Silurian had set the stage. Seas had recovered, reefs flourished, plants had ventured onto land, and arthropods had taken their first hesitant steps among the greenery. Now, in the Devonian period, spanning roughly 419 to 359 million years ago, life took bold strides. The oceans were no longer calm nurseries of simple fish. They became arenas of diversity, predation, and innovation. On land, plants grew taller, forests began to spread, and vertebrates took the first tentative steps onto solid ground. The Devonian is often called the Age of Fishes. This is no exaggeration. In every shallow sea and reef, fish dominated, experimenting with forms and strategies that would shape vertebrate evolution for millions of years to come. Among them were the placoderms, heavily armored fish with bony plates covering their heads and thoraxes. Many were formidable predators. Dunkleosteus, one of the largest, could reach 10 meters in length and crush prey with a jaw strength unmatched by most modern fish. Their dominance marked a new era of predator-prey dynamics in the oceans. Alongside them swam the early sharks, primitive but effective hunters, with sleek, cartilaginous skeletons adapted for speed and agility. Lurking among reefs and in open waters were also the lobe-finned fish, Sarcopterygians, their fleshy, muscular fins allowing them to push against the substrate, a hint of the terrestrial mobility that would come later. Jawless fish, the ancient survivors from earlier periods, still existed, but their role in the food chain diminished as jawed fish diversified. Invertebrates continued to thrive. Trilobites, mollusks, and eurypterids patrolled the waters, while corals and sponges built massive reef structures that were home to countless species. On land, plants evolved rapidly. The simple moss-like pioneers of the Silurian were joined by taller, more complex species. Cooksonia persisted, but new vascular plants, capable of transporting water and nutrients more efficiently, allowed forests to form. Among these was Archaeopteris, an ancient tree-like plant that could grow up to 30 meters tall. With true roots anchoring it in the soil, a woody trunk supporting branches, and leaves capable of photosynthesis, Archaeopteryx created the first forests. These forests transformed landscapes, stabilizing soils, moderating climates, and creating habitats for future land animals. The spread of forests had a profound impact on the atmosphere. Carbon dioxide was absorbed by plants at a much faster rate, while oxygen levels increased. By the late Devonian, the air had changed significantly compared to previous eons, creating conditions conducive to the evolution of larger terrestrial animals. Insects and other arthropods took advantage of the new greenery. Primitive millipedes and centipedes roamed the forest floor, feeding on decaying plant matter and fungi. Early arachnids, including ancestors of spiders and scorpions, hunted these arthropods, creating the first terrestrial food webs. The interaction between plants and arthropods marked the beginning of true terrestrial ecosystems. Plants provided shelter, food, and oxygen. Arthropods facilitated pollination, decomposition, and nutrient cycling. For the first time, life on land began to mirror the complex interactions seen in oceans. The Devonian seas also witnessed a critical evolutionary step: the development of tetrapods, four-limbed vertebrates capable of moving onto land. Lobe-finned fish, such as Eusthenopteron and Tiktaalik, developed robust fins with bones resembling wrists and elbows, allowing them to support their bodies in shallow water or mudflats. Tiktaalik, often called a fishapod, combined fish features, gills, scales, fins, with tetrapod traits, including a flat head, neck, and limb-like fins. These adaptations allowed it to explore the edges of water, venturing onto land to feed, escape predators, or move between pools. It was a transitional form, bridging the gap between fish and amphibians, and a milestone in the conquest of terrestrial environments. The Devonian was also a time of tectonic activity. Continental plates continued their slow drift, and collisions shaped new landmasses. Laurentia, North America, Baltica, Northern Europe, and Avalonia began converging to form Euramerica, a proto-continent that would later merge with Gondwana to help form Pangea. These collisions uplifted mountains, altered climates, and created new habitats for plants and animals alike. Coastal areas expanded, rivers carved valleys, and nutrient-rich sediments washed into the seas, supporting thriving marine life. Tectonics and biology intertwined, each shaping the other in an intricate dance. The Devonian was not without its crises. Toward the late Devonian, a series of extinction events occurred, disproportionately affecting marine life. Reef ecosystems were devastated, placoderms declined, and certain fish lineages vanished. The causes are debated. Some suggest rapid climate fluctuations. Others point to widespread anoxia in oceans, or ecological competition with emerging species. Despite these setbacks, the groundwork for future evolution remained. Tetrapods persisted, plants continued to expand, and the seas, though altered, still harbored abundant life. The Devonian was both a period of flourishing and of challenge, a dynamic era that bridged early complex life with the expansive ecosystems of the Carboniferous and beyond. By the close of the Devonian, Earth had changed dramatically. The oceans teemed with diverse fish, from jawless survivors to formidable predators. Reefs had grown vast and complex, shaping marine ecosystems. Plants had conquered the land, forming the first true forests and stabilizing soils. Arthropods had established terrestrial food webs, and tetrapods were on the verge of fully venturing onto land. Continents were shifting, colliding, and setting the stage for the assembly of supercontinents. The Devonian was a world of innovation, adaptation, and expansion, a world in which life boldly left its watery cradle and began to dominate the land. And as the Carboniferous dawned, these trends would accelerate, producing towering forests, giant insects, and oxygen-rich skies, ultimately leading to Earth's next great chapter in the story before Pangea. The Devonian had ended with innovation and turmoil. Fish had dominated the seas. Tetrapods were beginning their tentative steps onto land, and plants had forged the first true forests. The Carboniferous period, spanning roughly 359 to 299 million years ago, picked up the story and pushed life even further. It was a time of opulence and gigantism, when Earth's landscapes were dominated by towering forests, its skies filled with enormous insects, and life flourished in a world reshaped by high oxygen levels and shifting continents. The Carboniferous earned its name from the vast coal deposits that formed during this period. Across tropical and subtropical regions, low-lying wetlands and swamps stretched for hundreds of kilometers, creating ideal conditions for plant growth. Forests were dominated by lycophytes, sphenophytes, and ferns, some of which grew to astonishing sizes. Lepidodendron, a tree-like lycophyte, could reach over 30 meters in height, with scaly bark and dense canopies. Calamites, relatives of modern horsetails, form thick, segmented forests along rivers and floodplains. These forests produced vast amounts of organic matter, much of which fell into swampy waters, eventually compressing over millions of years into the coal seams that fuel modern industry. The forests weren't just tall, they were dense and humid, creating unique microclimates. Shade-loving plants thrived beneath towering canopies, while insects and early amphibians made their homes among roots and fallen logs. These ecosystems were the first to approach the complexity of modern forests, with layers of plants, decomposers, and herbivores interacting in intricate webs. One of the most striking features of the Carboniferous was gigantism among arthropods, particularly insects. Dragonflies with wingspans exceeding 70 centimeters, patrolled swampy rivers. Millipedes, such as Arthropleura, could grow up to 2.5 meters long, the largest known terrestrial arthropod in Earth's history. The driving force behind such gigantism was the atmosphere itself. Oxygen levels were extraordinarily high, perhaps 35% compared to today's 21%. With more oxygen in the air, insects could grow larger because their tracheal breathing systems could deliver sufficient oxygen to their tissues. Imagine the first forests, foggy, humid swamps filled with massive dragonflies swooping over rivers, giant millipedes crawling along the forest floor, and the first amphibians lurking in shallow pools, hunting prey. Life on land had truly come into its own. Tetrapods that had evolved in the Devonian now diversified into various forms. Some remain tied to water, like Acanthostega, with limbs suitable for paddling and walking short distances on muddy banks. Others, like Ichthyostega, were more robust, capable of venturing further onto land. These early amphibians preyed on insects, smaller arthropods, and other vertebrates, establishing the first terrestrial predator-prey dynamics. Their skin was permeable, so they required humid environments to survive, which is why the lush Carboniferous swamps were ideal habitats. The Carboniferous marked the first significant radiation of terrestrial vertebrates, setting the stage for the amniotes of the Permian, which would eventually lead to reptiles, birds, and mammals. Geologically, the Carboniferous was a time of continental movement and collision. The continents that had been scattered, Laurentia, Baltica, Avalonia, and Gondwana, moved closer together. Collisions formed mountains and highlands, reshaped rivers, and influenced climate patterns. The supercontinent Pangea was slowly assembling. Tropical swamps dominated equatorial regions, while more arid environments emerged toward the edges of the continents. These shifting habitats promoted adaptation and diversification, both in plants and animals. The climate was warm and humid overall, but glaciation persisted in southern Gondwana. Ice sheets waxed and waned, periodically lowering sea levels and influencing the distribution of coastal and swamp ecosystems. While life on land flourished, the oceans continued to teem with diversity. Reef ecosystems thrived, built by corals and stromatoporoids, but were also populated by brachiopods, mollusks, crinoids, and early sharks. Placoderms had mostly disappeared, but cartilaginous fish and lobe-finned fish persisted. Marine predators included early sharks and jawed fish, hunting smaller fish and invertebrates in reef-rich coastal waters. Meanwhile, the first ammonoids appeared, providing new prey for evolving predators and further diversifying marine ecosystems. The Carboniferous stands out not only for size and abundance, but also for the complexity of ecological interactions. Plants provided food and shelter for arthropods. Amphibians preyed on insects. Predatory fish maintained balance in the seas. Nutrient cycling, predator-prey dynamics, and interspecific competition were all becoming more intricate. This was a period when ecosystems became increasingly modern in structure. Each organism, whether in water or on land, played a role in an interconnected web, shaping the environment for future evolutionary milestones. By the late Carboniferous, the first amniotes, vertebrates capable of laying eggs on land, began to appear, setting the stage for the rise of reptiles. Forests continued to expand, insects continued to grow giant, and atmospheric oxygen remained high. The movements of continents toward Pangea were nearing completion. With terrestrial ecosystems flourishing and marine diversity rich, Earth was poised for the next chapter, the Permian period, where Pangea would finally assemble and life would face its most severe challenges yet. The Carboniferous was a time of growth, gigantism, and ecological experimentation. Life had mastered land and sea, evolved complex interactions, and established the foundation for the late Paleozoic world, a world that would soon converge into the mighty supercontinent Pangea. The Carboniferous had been a period of lush forests, giant insects, and burgeoning terrestrial ecosystems. As the world transitioned into the Permian period, approximately 299 to 252 million years ago, the story of life entered its most dramatic prelude to the Mesozoic. Earth's continents were converging into a single supercontinent, Pangea. This monumental tectonic process reshaped oceans, climates, and habitats, setting the stage for one of the most extreme challenges life would ever face: the Permian-Triassic extinction event, also known as the Great Dying. By the early Permian, Laurentia, Baltica, Siberia, and Gondwana were colliding. These continental collisions gave rise to massive mountain ranges. The Ural Mountains, forming as Siberia and Baltica collided. The Appalachians, continuing to rise from earlier Carboniferous collisions. Highlands and plateaus across parts of Gondwana. As these mountains rose, they influenced global climate patterns, altering wind and rainfall distribution. The formation of Pangea dramatically reduced shallow continental seas, leaving vast interior regions arid and dry. Unlike the lush Carboniferous swamps, large swathes of Pangea became deserts, creating harsh conditions for life. Despite this, coastal regions and river valleys remained productive. Marine ecosystems continued to thrive along continental margins, where nutrients flowed from eroding highlands into the seas, fueling reefs and invertebrate diversity. The Permian climate was highly variable, with pronounced arid zones in the continental interior and seasonal fluctuations elsewhere. Shallow seas receded, leaving isolated basins prone to salinity changes, while volcanic activity in regions like Siberia would later unleash massive eruptions that drastically impacted the global environment. Atmospheric oxygen levels, which had peaked in the late Carboniferous, began to decline slightly. Still, life on land had adapted to a variety of niches. Reptiles, amphibians, insects, and plants all diversified in response to increasingly challenging conditions. With drying habitats and the evolution of the amniotic egg, reptiles became the dominant terrestrial vertebrates. The amniotic egg allowed embryos to develop in protective shells with internal membranes, freeing vertebrates from dependence on water for reproduction. This innovation was critical for survival in arid environments. Early reptiles were small, agile predators and herbivores. Among them were captorhinids, small, agile, lizard-like reptiles; pelycosaurs, including the iconic Dimetrodon, with its distinctive sail likely used for thermoregulation. Pelycosaurs were apex predators in their ecosystems, hunting amphibians and smaller reptiles, while other pelycosaurs specialized in herbivory. These species exemplified the first true diversification of amniotes, setting the stage for the rise of therapsids, the mammal-like reptiles that would dominate later Permian landscapes. In the oceans, life remained diverse, but faced increasing environmental stress. Reefs, dominated by sponges and algae rather than corals, formed along continental margins. Brachiopods, mollusks, ammonoids, and echinoderms thrived, while early sharks and bony fish patrolled the seas. However, the shrinking shallow seas and fluctuating climates created stressful habitats, leading to local extinctions and changing community structures. The stage was being set for a catastrophic global event that would nearly wipe out life entirely. Plants adapted to drier climates by evolving more efficient water transport and spore protection mechanisms. Gymnosperms, the first seed-bearing plants, became increasingly prominent. Conifers, cordates, and ginkgo-like plants colonized vast stretches of Pangea's interior, replacing the swamp-dominated Carboniferous forests. These new forests were less humid and more open, creating environments suitable for reptiles to thrive, while amphibians became increasingly restricted to wetlands and rivers. Insects also diversified to match the changing plant communities, with early beetles, cockroaches, and other terrestrial arthropods exploiting new ecological niches. The Permian period culminated in the most severe extinction event in Earth's history, the Permian-Triassic extinction, around 252 million years ago. Up to 96% of marine species and 70% of terrestrial vertebrates vanished. Causes were multifactorial. Siberian traps volcanism. Massive eruptions released enormous amounts of CO2 and methane, leading to global warming and ocean acidification. Anoxia in oceans. Warming and stagnation caused oxygen-depleted zones, suffocating marine life. Climate extremes, rapid temperature fluctuations, and aridification devastated terrestrial habitats. Ecological collapse, predatory-prey relationships broke down, food chains were disrupted, and survivors were often opportunistic species adapted to harsh conditions. This extinction was profound, erasing dominant groups such as pelycosaurs, many amphibians, and marine invertebrates, while creating opportunities for survivors, early archosaurs, therapsids, and new plant lineages to diversify in the Mesozoic. Despite its catastrophic end, the Permian was a pivotal era. Pangea's formation unified most of Earth's land masses, reshaping ocean currents and climates. Reptiles, freed from water-dependent reproduction, diversified into ecological niches previously unavailable. Seed plants and gymnosperms established the first large, resilient forests suitable for dry conditions. Marine ecosystems, though severely impacted at the end, had reached a level of complexity unseen before. The Great Dying cleared the stage, making way for the Triassic period, when the Mesozoic world, dominated by reptiles and eventually dinosaurs, would rise from the ashes. From the earliest microbial mats of the Archean to the first forests and reptiles of the Permian, life had continually adapted, innovated, and expanded. By the close of the Permian, Earth had supercontinent Pangea almost fully assembled, shifting climates producing deserts, river systems, and coastal wetlands, reptiles occupying dry lands, amphibians limited to aquatic or moist habitats, plant life transitioning from swamp-dominated carboniferous forests to drier, seed-bearing flora. The extinction event of the Permian would reset ecosystems, allowing new groups to dominate and setting the stage for the Mesozoic era, the age of reptiles, and the eventual rise of dinosaurs. The Permian-Triassic extinction had left Earth scarred and empty, yet life is resilient. The survivors of this catastrophe, amphibians, reptiles, and early archosaurs, set the stage for a dramatic rebirth. By the early Triassic, approximately 252 to 247 million years ago, Earth had stabilized. The supercontinent Pangea dominated the planet, stretching from pole to pole and surrounded by the vast Panthalassa Ocean. Coastal areas were limited, while the interior of Pangea was dry and prone to extreme temperatures. These conditions challenged life, yet they also created opportunities for evolutionary innovation. Triassic Pangea was a vast land of extremes. The interior was hot and arid, with deserts extending for thousands of kilometers. River systems cut through these deserts, creating narrow corridors of life where plants, amphibians, and reptiles could survive. Coastal regions and shallow inland seas, though limited, supported marine and brackish ecosystems. Seasonal monsoons influenced rainfall in some regions, creating temporary wetlands and supporting early plant communities. The global climate was generally warmer than today, with polar regions milder than modern equivalents, allowing life to persist at higher latitudes. Plants recovered from the Permian extinction and adapted to Pangea's dry interior. Gymnosperms dominated, including early conifers, cycads, and ginkgo-like species. These plants were hardy, capable of surviving in less fertile soils and arid conditions. In river valleys and oases, ferns and horsetails flourished, creating patches of greenery amidst deserts. These plants provided food and shelter for herbivorous reptiles, insects, and amphibians, maintaining the first complex terrestrial food webs since the Great Dying. The Triassic saw the rise of the archosaurs, the group that would give rise to crocodiles, pterosaurs, and eventually dinosaurs. Early archosaurs were small to medium-sized predators, agile and well adapted to hunting in Pangea's varied environments. Among the survivors of the Permian were therapsids, mammal-like reptiles. Some remained small, nocturnal insectivores, while others grew larger and adapted to terrestrial ecosystems as herbivores or omnivores. These species represent the evolutionary lineage that would eventually lead to true mammals. Early dinosaurs began to appear in the middle to late Triassic, small and bipedal, hunting insects and small vertebrates. Examples include Eoraptor and Herrerasaurus, agile predators that exemplified the early success of dinosaurian evolution. Though the Triassic interior of Pangea was largely arid, the surrounding Panthalassa Ocean and scattered inland seas were full of life. Ichthyosaurs, dolphin-like reptiles, hunted fish in open waters, while placodonts, armored marine reptiles, grazed on shellfish along shallow reefs. Reef ecosystems, dominated by sponges and algae rather than corals, provided habitat for mollusks, ammonoids, and early crustaceans. Sharks persisted, and bony fish continued to diversify, including early ray-finned fish that would dominate Mesozoic waters. Terrestrial ecosystems of Triassic Pangea were defined by adaptations to arid conditions. Amphibians were largely confined to wetlands, whereas reptiles and archosaurs adapted to life in open, dry landscapes. Predator-prey dynamics evolved as early dinosaurs, archosaurs, and mammal-like reptiles competed and diversified. The interconnectedness of ecosystems began to mirror modern patterns. Plants supported herbivores, which in turn supported predators. Insects aided in pollination and decomposition. Rivers and oases became critical refuges, sustaining biodiversity in the vast Pangean deserts. The assembly of Pangea had profound geological effects. Mountains formed along collision zones, influencing rainfall patterns and creating isolated habitats that promoted speciation. Volcanism persisted in some regions, periodically reshaping landscapes and contributing to climatic fluctuations. As the Triassic progressed, tectonic stresses slowly fractured parts of Pangea, foreshadowing the eventual breakup that would create the Atlantic Ocean and reshape Earth's continents. The Triassic marked the beginning of the Mesozoic era, a time when reptiles dominated land, air, and sea. Early dinosaurs and archosaurs would eventually radiate into the dominant terrestrial animals, while marine reptiles and diverse fish thrived in the oceans. Plants had adapted to harsh conditions, forming the first large-scale gymnosperm-dominated ecosystems. Amphibians persisted in aquatic habitats, while insects and arthropods diversified to fill terrestrial niches. By the end of the Triassic, Earth was poised for the Jurassic, when dinosaurs would rise to dominance, forests would flourish in wetter climates, and Pangea would continue its slow fragmentation, giving rise to the continents we recognize today. The Triassic period had ended with the rise of early dinosaurs, archosaurs, and resilient ecosystems adapting to Pangea's harsh interior. Now, in the Jurassic period, approximately 201 to 145 million years ago, Earth entered a time of dramatic transformation, characterized by continental fragmentation, lush forests, and the spectacular radiation of dinosaurs across every landmass. By the early Jurassic, Pangea began to split apart. Tectonic forces stretched the supercontinent, creating rift valleys, shallow seas, and the nascent Atlantic Ocean. The splitting of Pangea formed two major landmasses: Laurasia, comprising what is now North America, Europe, and Asia; Gondwana, consisting of South America, Africa, Antarctica, India, and Australia. This fragmentation reshaped global climates. Increased coastlines allowed for greater rainfall in some regions, while inland areas became more temperate. The new shallow seas created corridors for marine life and influenced ocean currents, encouraging biodiversity in both terrestrial and marine ecosystems. Jurassic landscapes were lush and green. Forests dominated by gymnosperms, conifers, cycads, and ginkgo-like plants covered vast regions of Laurasia and Gondwana. Understory plants, including ferns and horsetails, flourished in the shadow of towering trees. The Jurassic forests were complex ecosystems. Trees provided shelter for small dinosaurs, insects, and early mammals. Fallen logs and dense undergrowth created microhabitats for amphibians, reptiles, and invertebrates. By creating vertical stratification, canopy, understory, and ground layer, these forests promoted biodiversity and interactions unseen in earlier periods. The Jurassic marked the golden age of dinosaurs, when they became the dominant terrestrial vertebrates. Herbivorous dinosaurs flourished, feeding on gymnosperms and ferns. Notable groups included sauropods, such as Brachiosaurus and Apatosaurus, with massive bodies, long necks, and tails. These giants could reach heights of over 20 meters, feeding from the treetops and shaping plant communities. Stegosaurs, plated herbivores with spiked tails for defense. Predatory dinosaurs also diversified. Allosaurus, a large carnivore capable of hunting sauropods in coordinated groups. Smaller theropods, agile and fast, preying on insects, small reptiles, and juvenile dinosaurs. This era also witnessed the rise of social behavior in some species, with evidence of herding, nest guarding, and coordinated hunting strategies. In the skies, reptiles took to flight. Pterosaurs, the first true flying vertebrates, dominated aerial habitats. With wings formed by a membrane stretched along an elongated fourth finger, they soared over Jurassic forests and coastlines, hunting fish and small terrestrial animals. Birds began to emerge later in the Jurassic. Early avian species, such as Archaeopteryx, exhibited a mix of feathers, wings, and reptilian features like teeth and long tails. These creatures represented the evolutionary bridge from small feathered theropods to modern birds, hinting at the incredible diversity yet to come. Jurassic seas were vibrant and diverse. Ichthyosaurs, streamlined and fast, hunted fish and cephalopods. Plesiosaurs, with long necks and powerful flippers, glided through shallow seas, preying on fish and other marine reptiles. Ammonites, the spiral-shelled cephalopods, were abundant and served as a key prey species for marine predators. Coral reefs, constructed by Scleractinian corals and sponges, flourished along coastlines. These reefs provided habitat for fish, invertebrates, and small marine reptiles. Marine ecosystems became increasingly structured, with complex predator-prey relationships and ecological niches resembling modern oceans. The Jurassic period was a time of evolutionary experimentation. Dinosaurs developed specialized teeth, jaw structures, and digestive systems for diverse diets. Feathers began to appear on small theropods, initially for insulation or display, later enabling flight in avian lineages. Pterosaurs evolved flight adaptations, including elongated wing fingers, hollow bones, and aerodynamic skulls. Marine reptiles perfected swimming adaptations, with flippers, streamlined bodies, and sophisticated hunting strategies. Global climates during the Jurassic were generally warm and humid, promoting forest growth and supporting rich terrestrial ecosystems. Shallow epicontinental seas warmed, creating productive marine habitats. High sea levels flooded lowlands, while continental interiors remained temperate, supporting large dinosaur populations. Volcanic activity associated with Pangea's rifting influenced local and global environments. Lava flows, ash deposits, and localized climate effects created both challenges and opportunities for evolving species. Jurassic ecosystems were complex and interconnected. Herbivorous dinosaurs shaped plant communities through grazing and browsing. Predators controlled herbivore populations, influencing behavior and migration patterns. Flying reptiles and early birds occupied aerial niches, hunting insects, fish, and small terrestrial vertebrates. Marine reptiles regulated fish and cephalopod populations, while reefs provided shelter and food for a multitude of organisms. These interactions created the first truly modern terrestrial and marine ecosystems, setting the stage for the apex of dinosaur dominance in the Cretaceous. By the close of the Jurassic, Earth had transformed dramatically. Pangea's fragmentation created Laurasia and Gondwana, altering climate and ocean circulation. Forests had expanded and diversified, supporting intricate food webs. Dinosaurs had risen to dominance, with herbivores and predators shaping ecosystems. Marine reptiles, ammonites, and fish thrived in productive oceans. Early birds and pterosaurs took to the skies, representing a new frontier of vertebrate evolution. The Jurassic was a period of expansion, innovation, and diversification, a bridge from the terrestrial recovery of the Triassic to the unparalleled dinosaur ecosystems of the Cretaceous. Life was flourishing on every continent, in every ocean, and even in the skies, a vivid prelude to the stories yet to unfold. The Jurassic had given rise to the spectacular age of dinosaurs, sprawling forests, and the first true flying vertebrates. Now, in the Cretaceous period, approximately 145 to 66 million years ago, Earth entered its final chapter of the Mesozoic, a time of extraordinary biodiversity, continental separation, and evolutionary innovation. By the early Cretaceous, the fragmentation of Pangea was largely complete. Laurasia and Gondwana had drifted further apart, creating the Proto-Atlantic Ocean. The Tethys Sea divided northern and southern continents, influencing global climate and ocean circulation. These changes produced warmer, wetter climates in coastal regions and temperate interiors, shaping ecosystems across the planet. The breakup of continents created diverse climates. Coastal plains flourished with lush forests, wetlands, and river systems. Deserts expanded in interior regions of Gondwana, while highlands and mountain ranges influenced localized rainfall patterns. The Tethys Sea acted as a warm equatorial corridor, allowing marine species to disperse between northern and southern hemispheres. This mosaic of habitats promoted the diversification of life. Plants, insects, and vertebrates each adapted to the new conditions, evolving novel strategies for survival. As continents drifted, populations became increasingly isolated, leading to speciation and the emergence of regionally distinct faunas. The Cretaceous marked a revolution in plant life, with the emergence and rapid spread of angiosperms, the first flowering plants. Unlike gymnosperms, which dominated Jurassic forests, angiosperms produced flowers, fruits, and seeds enclosed within protective structures, facilitating more efficient reproduction and dispersal. Ferns, cycads, and conifers persisted, but flowering plants began to dominate many landscapes, forming understory vegetation and creating diverse ecosystems. Their flowers attracted early pollinators, bees, beetles, and other insects, triggering co-evolutionary relationships that would shape terrestrial ecosystems for millions of years. Forests became increasingly stratified. Tall conifers formed canopies, flowering plants filled the understory, and ferns carpeted the forest floor. This vertical complexity supported a wider array of herbivores and small predators, establishing intricate food webs unseen in earlier periods. The Cretaceous is renowned as the pinnacle of dinosaur evolution, with species radiating into countless ecological niches. Herbivorous dinosaurs flourished, exploiting the diversity of plants. Hadrosaurs, the duck-billed dinosaurs, grazed in herds across plains and floodplains. Their complex dental batteries allowed efficient processing of tough vegetation. Ceratopsians, including Triceratops, evolved horned skulls for defense and display, often living in herds to protect against predators. Sauropods, enormous long-necked giants, reached their largest sizes, feeding from treetops and altering plant communities through browsing. Predatory dinosaurs also reached new heights. Tyrannosaurs, apex predators in Laurasia, hunted large herbivores with powerful jaws and keen senses. Smaller theropods, feathered and agile, occupied niches hunting insects, small vertebrates, and juvenile dinosaurs. Dromaeosaurs and other maniraptoran dinosaurs exhibited advanced hunting behaviors, including pack coordination and strategic ambush. The Cretaceous marked an era of ecological sophistication. Social behaviors, herding, nesting, and parental care became more prevalent among dinosaurs, indicating complex interactions within species. Feathered theropods continued to diversify. Early birds, descendants of small maniraptoran dinosaurs, became more abundant and varied. Species such as Confucius ornis displayed primitive beaks, wings adapted for flight, and feathers used for display or insulation. These early birds occupied niches ranging from forest understories to open plains, hunting insects, scavenging, and perhaps feeding on seeds. Flight allowed them to exploit resources inaccessible to non-flying dinosaurs, highlighting the adaptive advantage of feathers and the evolutionary experiments leading to modern birds. Cretaceous oceans teemed with life. Ichthyosaurs, which had dominated the seas during the Jurassic, were in decline, replaced by mosasaurs, massive marine reptiles capable of hunting fish, ammonites, and other marine reptiles. Ammonites continued to thrive, displaying a variety of shell shapes and patterns, serving as both prey and ecological indicators of ocean health. Reef ecosystems flourished along coastlines, built by scleractinian corals, sponges, and rudous bivalves, creating complex habitats for fish, invertebrates, and small marine reptiles. Marine food webs grew increasingly intricate. Predatory fish hunted smaller fish and cephalopods. Mosasaurs and plesiosaurs patrolled coastal waters, and plankton blooms fueled the base of the marine food chain. Cretaceous ecosystems were marked by sophisticated interactions. Herbivorous dinosaurs influenced plant evolution, dispersing seeds and shaping forests. Predatory dinosaurs regulated herbivore populations, promoting natural selection and social behaviors. Birds and small theropods controlled insect populations and acted as seed dispersers. Marine reptiles maintained balance in oceanic ecosystems, while ammonites and fish responded dynamically to predation pressures. Life had reached a level of ecological complexity reminiscent of modern ecosystems, with each species occupying specific roles and contributing to the dynamic balance of habitats. The Cretaceous was a time of high global sea levels, flooding continental interiors and creating epicontinental seas. Warm, humid climates prevailed in most regions, while seasonal aridity persisted in some continental interiors. The breakup of continents enhanced ocean currents, distributing heat and nutrients and supporting diverse marine ecosystems. Volcanism, especially along rift zones and subduction margins, influenced local and global environments. Lava flows, ash deposits, and volcanic gases periodically affected climate, creating both challenges and evolutionary pressures for plants and animals. The Cretaceous was the culmination of Mesozoic life on land, in the seas, and in the skies. Dinosaurs dominated every terrestrial ecosystem. Marine reptiles ruled the oceans, and early birds filled the skies. But life was more than just size. It was innovation, interaction, and adaptation. By the mid to late Cretaceous, apex predators such as Tyrannosaurus rex in Laurasia epitomized carnivorous efficiency. These predators were massive, with jaws capable of crushing bone, keen senses for hunting, and social behaviors that may have included pack hunting. Other large theropods, such as Carcharodontosaurus in Gondwana, occupied similar ecological roles, highlighting convergent evolution across continents. Herbivorous dinosaurs were equally impressive. Sauropods, including titanic genera like Argentinosaurus and Alamosaurus, shaped entire ecosystems through browsing, trampling, and seed dispersal. Herding behaviors in hadrosaurs and ceratopsians allowed coordinated defense against predators, with adults protecting juveniles, while juveniles learnt survival skills within social groups. Evidence from nesting sites shows that dinosaurs practiced parental care. Fossilized nests of hadrosaurs and ceratopsians indicate eggs arranged in colonies, suggesting complex behaviors including protection, guarding, and possibly even teaching hatchlings. These social dynamics added a layer of ecological sophistication previously unseen in Earth's history. While dinosaurs dominated, mammals quietly diversified in niches under the radar. Small, mostly nocturnal, and insectivorous, early mammals such as multituberculates and primitive marsupials lived in burrows, forest undergrowth, and trees. These mammals were highly adaptable, feeding on insects seeds, and small vertebrates. Their small size, nocturnal habits, and rapid reproduction allowed them to survive in ecosystems dominated by reptiles. Although overshadowed by dinosaurs, mammals were laying the foundation for future evolutionary success after the Cretaceous-Paleogene extinction. In the oceans, coral reefs reached new heights of complexity. Scleractinian corals, rudous bivalves, sponges, and algae formed dense reef systems, providing shelter for fish, ammonites, small marine reptiles, and invertebrates. Marine ecosystems were structured with trophic hierarchies. Apex predators like mosasaurs and large pliosaurs hunted fish, cephalopods, and smaller marine reptiles. Mid-sized predators controlled fish populations and preyed upon ammonites. Herbivorous and filter-feeding species grazed on plankton and algae. This structure mirrors modern ocean ecosystems, indicating a level of ecological stability and complexity rarely seen in Earth's history. The Cretaceous was marked by intricate ecological interactions. Dinosaurs shaped plant evolution through selective feeding, seed dispersal, and trampling. Predators regulated herbivore populations, promoting herd behavior and social learning. Early birds and feathered theropods influenced insect populations and pollination. Marine predators, reefs, and invertebrates formed interconnected food webs that maintained balance in oceans. Early mammals occupied niches under dinosaur dominance, using nocturnal habits to survive and thrive. The result was a planet teeming with life, each species contributing to ecosystem stability while simultaneously driving evolutionary innovation. By the late Cretaceous, Earth had reached a peak of diversity. Dinosaurs were dominant, with ecosystems supporting apex predators and massive herbivores. Forests and flowering plants covered continents, creating complex terrestrial habitats. Marine ecosystems flourished, from shallow reefs to deep oceans. Birds and mammals diversified into small, specialized niches. Yet, this vibrant world faced a sudden and catastrophic challenge. The Cretaceous-Paleogene extinction event, triggered by an asteroid impact, volcanic activity, and climate disruption, would radically reset life on Earth, ending the reign of non-avian dinosaurs and paving the way for mammals to dominate. The Cretaceous represents the zenith of Mesozoic ecosystems, a time of ecological richness, evolutionary experimentation, and biological dominance. Dinosaurs perfected a wide range of adaptations, from colossal size to complex social behavior. Early birds and mammals diversified in response to ecological pressures, while flowering plants transformed terrestrial landscapes and ecological interactions. Earth at the end of the Cretaceous was a planet of extremes. Massive predators and herbivores roamed continents. Coral reefs pulsed with marine life, and forests stretched across continents. Every niche was filled, every ecosystem intricately balanced, until a sudden cosmic event would bring an end to this chapter of life.